Okay, what we are going to learn today is about, again, the neural network. Okay. You already learned about the basic neural network. So the neural network itself, if you know the flow, yeah, you can understand how it works. But now we need to define the network topology. What is the meaning by network topology? So when we deal with the network topology, it means we need to know what is the purpose of the neural network. So the neural network can be used for both classification. We know that the classification can be binary or multi-class. Binary means 0, 1. Multi-class, it can be more than 2 classes. Okay. Or prediction. Okay. So the prediction means the class is numerical. Decide the network topology. The network topology means you need to specify the number of units in the input layers. So if we have our data, then you need to specify, for example, I have 3 units in the input layers, or I have 5 variables in the input layers. And the other thing that we need to specify is the number of hidden layers. So if it is more than 1, then you need to specify. And you need to specify the number of each unit in its hidden layer. So we have the same number of the unit in each of these hidden layer. Let's suppose we have 1, 2, 3, 4 units in hidden layer 1. We have also another 4 units in the hidden layer 2. Then it is equal. But sometimes this hidden layer may have different units. And also the number of units in the output layer. So how many units in this layer? Whether you have 1 or we can have more than 1. It depends on the goal. If it is the classification, maybe if it is binary, then you can have only 1. But if it is multi-class, then there will be more than 1. And the other thing that we need to understand is the normalization. Normalize the input values for each attribute measured in the training tuples. Because we do not know the numbers, maybe the numbers can be related to price. And you may have another variable, for example, age. If the price is in the Korean won, then maybe can be like 10만원, 100만원, but the age range will be from 0 until 100. So the values will be very in the big gap. That's why we need to make the normalization value between 0 and 1 for the input values. So they have the similar grouping numbers, so you can use it for the order analysis. So one input unit per domain value is initialized to 0. So we can say that the initial value is 0, and then the output, if for classification and more than 2 classes, 1 output unit per class is used. So if we have more than 2 classes, usually we have the output unit more than 1. So this one, it means one output unit per class. So let's say if we have the iris, in the iris flower, how many classes do we have? We have three. Okay. Iris setosa, Iris virginica, Iris versicolor. So in that case, we need to have also three units. Okay. So one output unit per class. Once a network has been trained and its accuracy is unacceptable, so unacceptable means the accuracy is very low. Maybe the accuracy is only 30%, or the accuracy is only 40%. So it's very low because it is lower than 50. Then we can repeat the training process with a different network topology. For example, yeah, I think last week there was a question, how many hidden layers that is good? So we do not know. If the accuracy is unacceptable, then maybe we can add more hidden layers, or we can have different set of initial weights. Now it comes to a new kind of network, how the neural network is trained. We have one algorithm that is the most popular approach. We call it backpropagation. Backpropagation is a neural network learning algorithm. So learning here means the training. And the backpropagation learns by iteratively processing a data set of training tuples and then comparing the network's prediction for each tuple with the actual known target value. So I think you already know we have y is the actual value, and we have the y hat on y prediction. So this is always the case when you do prediction, when you do classification. You always compare whether the actual value is the same with the predicted value. For each training tuple, the weights are modified to minimize the mean square error between the network prediction and the actual target value. So if we use the regression, it means we have the y hat minus y. So if the error rate, or let's say I make it square, so if the error rate is low, then yeah, it is a good model. We can modification are made in the backwards direction. Backwards mean if we have the first network, we call it forward. The forward neural network means we start from the input to the output, but the backwards from the output layer through its hidden layer down to the first layer. So we return back from the output layer and go to the first hidden layer. We call it, this is the back propagation. So the training procedure will be something like this. The step one, we will initialize the weights. If you look at the example that we have before, the example shows the weight. How can we get the weight? Like this one. This is the weight. The weight. So in the first time, usually the weight is random. So the initialization of the weights, usually we have random. And then we will propagate the inputs forward. We apply the activation function. Maybe in this case, we will use the sigmoid function. Okay, so if you look at this one, this shows the forward, and then after we finish the forward, we will backward. So we can see from here, we go click forward until here, we return back to the input. So we call it, this is the back propagation. So if the cost is already low or the error is already low, then we can stop. So step 1, 2, 3 are repeated until terminating condition is satisfied. So it is when the error is very small, or when the percentage of tuples misclassified in the previous epoch is below some threshold, or a specified number of epochs has expired. And there are so many other conditions that you can determine. And this is the definition. Yeah, I use some Korean words from the Professor Sok. He, I think it is good if I use this terminology for you. If the English explanation is a bit difficult for you, the batch size. The batch size means the number of training samples utilized in one iteration. So let's say we have batch size is 100. Then one time of the training, it takes 100 frames of video processing. So if we specify 100, then we will take 100 data. So it depends how you define this number. And those number, we need to specify by ourselves. Maximum iteration, max iter. It is the maximum number of iteration taken for the solvers to converge. So let's say I have the batch size is 100, and then I want to, this 100, it is in one iteration. So I can do another iteration, and I'm specifying that the maximum iteration is 50,000. Then we will do the iteration for every 100 frame of the video until 50,000 iteration. We have test iteration. It indicates how many times the learning result, or we call this is the testing result, are checked. We can use the same batch size, and we can specify what is the testing iteration. Epoch. It indicates how many times you use the entire learning tuple to learn. So let's say I have, maybe you can have this one. For the total data set, I have like 50,000, okay, and I want to specify for the batch size is 100. Then I can say that, let's say the training set is 40,000 and the testing is 10,000. So because I'm specifying the batch size is 100, then there will be like 5 million times, and we have 40,000 training sets. Then it will make you to have like 125 people. Okay. So this number is based on the 50,000 data, and this 50,000 data will be split it into the batch size 100, and then we will divide with the number of the training set. There will be another kind of parameter, learning rate. It really depends on the problems. Usually we use the learning rate with a very low number, because if it is too large, it will overshooting, or the overshooting takes too long. So let's see from this one. So let's say I have like 2000 data. Maybe this is the very simple way to explain. I have 2000 data, and then for usually we can define like the iteration takes 10 times. Then the network will automatically assign for every batch, it will be like 200. Or you can specify, if I want to have the batch size 200, then the network can automatically do the iteration 10 times. So it depends how you define this parameter. And we call this is one epoch. So if we already finished with one epoch, then we can again do with different 200 data for every batch size. And after we finish with all the iteration, then we call this is the epoch number 2. And you can run again until how many epochs you want to run. The high epoch, of course, it will give you the reliable networks, but it costly about the time. So you can see from this diagram, when you assign with a random weight at the first time, maybe the error rate is still very high. But when we did the backpropagation, the error rate, it becomes lower and lower and lower and lower until we reach the global optimum. So we call this is the, you can see, this is the descending with the start coefficient 0.05. And this is the descending with the start coefficient 0.05. So if the learning rate is lower, usually we can see this one will convert smoothly like this. But if it is a little bit high, then there will be many times to check until the global optimum. So how to determine the learning rate? This is still, there are some optimization algorithm to do this one, but I will not discuss it. So you can use like the Adam optimizer, some optimization approach already established in this neural net. So if we have the very high learning rate, so the number of epochs will be very, very high. If you have a low learning rate, then maybe the loss will go with a very good loss numbers in a particular epoch. If you use the high learning rate, so it may take sometimes until the loss lost. So the problem is now how we can define the good learning rate. This is the algorithm of the backpropagation. Maybe it's better to see the examples rather than seeing this algorithm. So we have this network. Okay. We have the input layer, we have the hidden layer, and we have the output layer. Now you can see there are 3 units, x1, x2, and x3. And for every unit, there is a connection with the hidden layer. W14, it means it is the weight from the unit 1 to the unit 4. W15, it is the weight from the unit 1 to the unit 1. And so on. We have W24, W25, W34, W35, and we have bias. We say this is the theta 4, and we have this one theta 5. We have another weight here, and we have the theta 6. The last one is the probability of the class being the class equal to 1. So if you look at this one, we can say that this is binary classification because we have only one unit. So the parameters numbers you can see from here. So we have the initial input, which is 1, 0, 1 for x1, x2, x3. And then the weight 1,4 is 0.2, weight 1,5 is minus 0.3, weight 2,4 is 0.4, and so on. So those numbers we can generate random. So let's just put all the numbers like this one. 1, 0, 1. It is the initial value for the input. And then we have all the numbers as the weight. And we have the bias. We have the weight. And this is the bias. So how this network works? You already learned how to calculate the basic network in the previous examples. Now, let's try to figure out more with the activation function. What does it mean by the activation function? As you might know, in the previous example, we have only the input, and then we just do the weighted sum. The weighted sum means if this value is 1, we multiply with the weight, and then plus. Let's say this one is the 1, and then we multiply with the weight, and then plus. Let's say this one is 0, we multiply with the weight, and then we do the plus, the summation. The summation for these three, x1, x2, and the x3, we call this is the weighted sum. And then we need to add the bias. We do not consider the activation function in the previous example. So today we are going to use one activation function. We call it, this is the sigmoid or logistic activation function. OJ means the output. The output will be 1 divided by 1 plus E. E is a number, the natural number, power of minus IG. So in the exam, I will give you one problem like this. So please remember to bring your calculator because you need to calculate this natural number. So if you don't bring calculator, you may have difficulties to answer the problems in the final exam. So we have this notation. J is the hidden or the output layer on unit J. The IJ means the input value. OJ is the output value in unit J. OI is the output unit I in the previous layer. WIJ is the weight, and the theta is the bias. So I can do the weighted sum because this is the weighted sum, because every of the weight will be multiplied with the O, and we do the summation and plus the bias. And then we have this sigmoid function. So what we can do now, let's see one example. we have this 1, 0, and 1, and we want to find out how the network in the unit form comes out. So it means we have 1 multiplied by 0.2, 1 multiplied 0.2 plus 0 multiplied 0.4, 0 multiplied 0.4 plus 1 multiplied minus 0.1, 1 minus 0.1. And then we need to add the bias. This is the bias, minus 0.1. So the result will be minus 0.7. So you can calculate this one. Then after we have this minus 0.7, we will apply this formula. How to apply this one? It is the 1 divided by 1 plus E, this is the natural number, power of minus Ij. The Ij is minus 0.7. Then because it is minus minus, we have the positive. So we have the 1 divided by 1 plus natural number power of 0.7. Then the result is this number 0.332. And we put this one as the value in this unit form. Next, we need to calculate the unit 5. What is this unit 5? The idea is the same. We have this from 1, 2, and 3, and we know that this is 1, 0, and 1. We just multiply. 1 multiply minus 0.3, 0 multiply 0.1, 1 multiply 0.2. And then we add the bias, which is 0.2. So this will be the value, 0.1. Again, we put the activation function. So the activation function will be 1 divided by 1 plus the natural number power of minus Ij. The Ij is 0.1. Then we have like this. So you can get the value is 0.525. Then it will be the number in this unit. After we have the number here, 0.332 and 0.525, we can calculate the output in the unit 6 because we already know this number. So we have this number 0.332 multiplied by minus 0.3 plus 0.2 multiplied by, oops, I think I missed this one. Should be 0.525. Okay, I'm sorry. This one should be 0.525. Then we minus 0.1, which is the bias. So the value, I guess the value is still the same. Maybe I just mistyped it. Okay, anyway, this should be 0.525. And again, we will do the activation function. The activation function is 1 divided by 1 plus the natural number minus the Ij. We have this one, we have this number, then it is minus minus 0.105. Because it is minus minus, so we can have this is the positive number. And the result is 0.474. we can calculate the error. How we calculate the error is, it depends on how you define this problem, whether it is the classification or whether it is the prediction. And now there is one error formula that has been defined in this network. The error will be the OJ multiplied by 1 minus OJ multiplied by TJ minus OJ. So the OJ is the actual output of unit J, and TJ here, the TJ is the known target value of given training tuple. The target value, if we have like this binary, because this is the probability of being class 1. So if the probability is high, it means I have a certainty that this class is belong to class 1. If the probability is low, then I have a certainty that this class belong to 0. Then I will calculate this error. I know the output, which is 0.474, and then I will do this formula minus 1 minus 0.474, and then TJ, the target value. So the target value is 1, then we have 1 minus 0.474. And this is the error rate for this one. Now I have this error. So the idea is how we can minimize the error. Then we can check. The next is to define the error from the previous network. With the same formula, we have this error. The output is 0.525 multiplied by 1 minus 0.525. And now we are going to include the error rate from the latest one. So it means we want to check whether this error affect to this error rate. And later on, if we can have these error numbers, we can try to improve the network. So here I would like to measure the 0.1311 multiplied by the weight of this network. This is the summation. It means if we have only one, we can just do only one. But if there are more than one, let's say this network is, let's say if there is another bit forward like this one, then it means we need to deal with this one and the error rate from this one. So we do with this summation. Because we have only one, so we have only this formula, 0.1311 multiplied by minus 0.2. So the error rate is 0.0065 for the node 5. And then again, we do the same for this error. It means we calculate the output, which is the 0.332, 1 minus 0.332, and then we multiply with the error rate in the node unit 6 multiplied by the minus 0.3, which is the weight from 4 to 6. So this is the number. We put the error in the unit form as this number. So we can make the error for the remaining nodes. So we can say that the backpropagation also works for the previous one. We can also check the error. So if you finish until the first hidden layer, then now we are going to update the weights. How we do the updating? The updating will take place to check the delta. The delta Wij, it means it will be the learning rate multiplied by the error J multiplied by the OI. So the Wij or the new Wij, if you learn in programming, you will know that A equals to A plus B. It means the new A equals to the OA plus B. So this is the current value and this will be the new value. So here I would like to have the new weight, and the new weight will be based on the previous weight plus the delta Wij. The delta Wij we can get with this formula. So for example, I would like to update the weight for 6. How can I update this one? Let's suppose maybe just for the simple calculation, I will use the L. L is the learning rate. I use 0.9. This is just a very simple calculation. If you put very small number, yeah, it will be difficult to calculate it. But this is just to show the example. So the weight 4.6, it means I want to update the previous weight is minus 0.3. The previous weight is minus 0.3. And then I would like to plus with the delta Wij. The delta Wij, it means it is the learning rate, which is 0.9. I define here 0.9 multiplied by the error, which is the error of the node in this output, which is 0.1311 multiplied by the output, which is 0.332. So the weight will be this one for the new weight of 4 to 6. What about, let's say, W56? The W56, the previous weight is minus 0.2 plus multiplied by the learning rate 0.9. 0.1311 is the error rate in the node 6 and multiplied by the output of that particular node, the output of this node, which is 0.525. So this will be the new weight for 5 to 6. So this will be the new weight for 5 to 6. Now let's see just one example, W14. So in the W14, we know that the previous weight is 0.2. So I'm going to update it by plus learning rate, which is 0.9, multiplied by the error in this node, which is minus 0.0087, multiplied by the output of this node, which is 1. Then the weight will be updated to 0.9192. So the weight will be updated to this number. And so on. You can look at this number. Hopefully I didn't mistype. And after you define for the new weight, you also need to update the bias. You need to update the bias. How to update the bias? The bias will have their own formula. In this case, we just have the bias, the previous bias, which is 0.1. So here is the bias 0.1. Oh, this is minus 0.1. Oh, I didn't put the formula of this bias. Where do I put this? Okay, so if you look at this formula, yeah, I put here. So the delta bias equals to the learning rate multiplied by the error. Okay. So we do not need to multiply with the OI because we don't have any effect to the output of that node. So the difference between the weight and the bias is only the OI. We don't need to consider the OI. So here, the bias here is 0.1. I guess this is wrong. This should be minus 0.1. This one should be minus 0.1. Or maybe I mistyped this one. This should be 0. Sorry, too many mistyping. This should be 0.1. Then this will be 0.1, the previous bias, plus 0.9, which is the learning rate, multiplied by the error. This is the error in the node 6. So the new bias will be 0.218. Okay. And so on for this one, 0.2, and this is 0 or minus 0.4. So after we have this new bias, we put it into the respective node. What next? So we will do again the feed forward. And again, if we finish, we will do the backward until we get the lower amount, or until we finish how many epochs, or until we finish how many iterations that we want to do. Yeah, this neural network has some weaknesses. It is long in the training time because it depends how many layers, and it requires a number of parameters. So as I mentioned to you, yeah, we need to define how many layers or how many, what is the learning rate, and then how many epochs, how many iteration, and so on. And poor interpretability. So it is difficult to interpret the meaning. What is the meaning by the weight? What is the meaning by the hidden units? So it is not interpretable. But the strength is it is high tolerance to noisy data, and it is able to classify the untrained patterns. So if it is not in the training data, it can be, yeah, sometimes it can be done. And it is very good for continuous value input and output. And there are many good stories for the handwritten letters. The algorithms are inherently parallel, and now there are many techniques to extract the trained neural network. So we can just use the existing neural network, and we can do further with the existing pre-trained neural network. Okay, that's what we learned on this neural network. So we will move to another chapter on this Thursday. And this coming Thursday, there will be also another learning check. Please try to review what we already did today. Okay. Any questions, comments?